All right, let's get started. This is our last guest speaker from outside of economics, and one of the things that's been interesting over the last couple of days is the discussion of the variation in how machine intelligence is making its way into industry. And there's been quite a bit of discussion about the concentration of machine intelligence in the high-tech companies, like the Ubers and Googles and Amazons, as well as machine intelligence coming into manufacturing by way of intelligent robots. But as Tim Bresnahan reminded us this morning, that the role of machine intelligence in sort of the traditional industries is obviously important, and perhaps going back to Eric and his co-author's paper in 2017, why aren't we seeing this showing up in the productivity statistics? That they go through a number of hypotheses, and I think their conclusion is investments in complementary assets take time. And so what we wanted to do in our final guest speaker is to get inside the channel and the mechanisms through which machine intelligence is making its way into large, established, traditional businesses. And so our guest speaker is doing precisely that. He's the Chief AI Officer for a $140 billion business. It's a bank. And so what he's going to talk to us about is how machine intelligence is rolling into the bank. And what I think you'll find interesting, and to put his comments in context of who he is. So he's not a banker. And he is a computer engineer and an entrepreneur. He has been through this multiple times before, so he's built companies and sold them. He's sold a company to Yahoo. He's built and sold a company to Microsoft. He's also has he's been into machine intelligence before it became fashionable. And so for example, the project that he was leading at Microsoft Bing in 2011 was, which was in web search scoring, was, I think, regarded by many as the largest machine learning application in the commercial enterprise in 2011. After that, he started another startup company, which was actually focused on applying machine intelligence to predict preferences of people in the area of music. And that morphed into a company that they call Layer 6. Layer 6 was a bunch of machine learning gunslingers. They twice were champions of something called the ACM RecSys, which is the Recommendation Systems Conference, with the prediction engines that they built. And Layer 6 was a still pretty young company, as far as I could tell, marginal number of people, 20 or so people, marginal revenues, and they were acquired for about $100 million by the bank to bring AI into TD. And so we're going to have our speaker, Tomi Poutanen, who led that, come and talk to us about bringing AI into the bank. But I also wanted to ask him, because we sort of a unique opportunity for somebody who lives in that world. He's attended much of the conference, and so he's heard us and the problems that we work on in terms of economics of AI. And so I've asked him, before he begins his remarks, if he could just weigh in on his impression of what we're working on. So in other words, in what areas does he see us and say, wow, they are really naive and going off in a very, what would appear to at least a person who works in this domain, they're barking up the wrong tree, versus, what are the areas where he's surprised that, wow, the economists have, thought about this in a way that we've never thought about it, and that seems to make a lot of sense. So I asked him before he began his remarks, since he's spent a fair amount of time yesterday and today, if he could just weigh in with his observations from a person who's a computer engineer and actually deploying these in a large commercial setting for his reactions to our conference, and then his remarks of bringing the AI into the bank. Please join me in welcoming Tomi Poutanen.
There we go. Can you guys hear me back there? I'm not sure if this is there. Here we go. Yeah, so way to make friends. So where are you guys going wrong? First, let me just reflect on the conference itself. I love the format. I love this discussion and challenger format that you have. Very different from the computer science conferences, AI conferences specifically, where a lot of progress is being presented, but there's not a lot of debate on it. And the QED is proven empirically by better results in some data set without really understanding even how the model works. But just because you're able to beat the benchmark, we're smarter than you because the algorithm says so. But there's not a lot of debate like what you've gathered here. So that's my first reaction to just being here. It's been wonderful watching it. With regard to some of the remarks that I've been hearing, just a few things that stand out that I think it's important for this group of individuals to discuss. First of all, we hear a lot about deep learning, TensorFlow, OpenAI DeepMind, and artificial general intelligence. I think before OpenAI brings us AGI and we become puppets, there's another much more important, there's another technology that's going to impact economies on the short term. And it's a machine learning framework called gradient boosting machines. So I feel that there's a bit of a disconnect here where a lot of people are talking about deep learning and AGI, where there's something else already happening today. So I'll actually talk about that a little bit as I go through my presentation. The second thing is around the impact, the scale of this impact. And we had an interesting debate. This last session was an interesting debate just now, where some people thought, a lot of jobs are going to be displaced. Other people say, well, people have thought about this before, and they actually aren't replaced. So where do we end up? I'm of the believer that a lot of jobs will be replaced. At acquisition, there's 18 of us at layer 6. The bank has 1,800 data scientists, very different skill sets. So it's amazing what machine learning with a competent few people can accomplish that a larger group can't. I think another analogy would be home appraisers in the US. It's a job category. You can look it up. 210,000 home appraisers at their peak, going to zero. This is Donald Trumpism, zero. As something like the Zillow Zestimate proves to be more worthwhile than a human appraiser driving up curbside and looking at a house. I think there's a lot of job categories that will just be wiped out by machines. And that data, you can't see today looking at your historical data. I see a lot of analysis here. You guys are looking at historical data, job categories over the last 10 years. That future is not yet indicative. The historical data doesn't yet predict where the future is going to go. I think there will be a tremendous amount of disruption. And the last conversation that's kind of perking up in my, that's interesting to me is this wealth distribution. Yes, large companies with lots of assets will disproportionately accumulate a lot of wealth. Same as with individuals. Machine learning at its core is a huge productivity booster, which means that those people able to benefit from it, are able to practice it, can just produce more value and will become prosperous for it. And that also means that there's a huge swath of the population that will not be able to participate in that value creation. Just because AI is going to come in and create such a huge step change in productivity that there's just not enough GDP to share, right? So that GDP is going to be captured by the organizations and the people that can successfully deploy AI. And that's within a nation, and you can see that wealth distribution between Idaho and, say, San Francisco. But it's also between countries. Say, if you're a country that's building AI versus buying AI, huge macroeconomic consequences from there. And those are conversations I didn't really hear today. There's also a sub-conversation from that is around how competition between big companies and small companies how will be impacted by the application of AI, and also how I think how antitrust laws should reflect this, privacy laws, immigration policies, all of these things are interrelated. All right, that was an engineer talking about economics. Let's go into this presentation. Let me just first say, Steve Jurvetson's talk, wow. I'm going to be bringing it down a notch, okay? This is about AI in banking, okay? But thankfully, this room actually cares about these types of things. So, but my perspective will be the following. My perspective is that of an engineer who built some of the very early machine learning systems at big tech companies. The perspective of an entrepreneur that looks to disrupt industry. And as Ajay said, the chief AI officer of a 85,000 employee bank. And you can add that into your list of new titles, Chief AI Officer. That title is actually a reflection of the bank's realization that AI will be disruptive. It will be a competitive advantage, and the AI priorities and strategies need to be driven from the top of the house. This is not something you bury inside of an analytics organization. The first decision a large organization has to make when it comes to AI is a build, buy, or partner strategy. TD chose to go down the path of acquiring. And it's not always an easy fit. Even a computer vision algorithm with an anomaly detection could say, this is a bit of a unusual thing. But I have to say the integration was very well done by TD Bank. They had, going into it, this was my biggest concern. Here's a bank. I'd never worked at a bank before. They had never bought a tech company before. What could possibly go wrong? I had sold my previous businesses to a big tech company in the West Coast. I've been on the buying side, and that's on the other side. Half the acquisitions go astray in some way. But at TD, it actually worked. It worked out really well. I think my main measure of whether it was going to work or not was, can I retain my people? Can I continue to grow? And to that, by that measure, we've managed to grow and prosper within this environment. Part of what makes us be able to do that is we've got great proximity to the Vector Institute of the Artificial Intelligence School here under Jeff Hinton in Toronto. And we also do a lot of work outside of banking. We do work with the healthcare sector. We were the first people to deploy deep learning into this amazing health data set that's in Ontario. So we've done a lot to make this a purpose-driven organization, not just one that profits the bank. So it's been really a lovely place to be. And this kind of shows that not only we got to be known because we won this competition on personalization systems called ACM Rexis. Before that, it was big tech companies that won it. We won it 2 years in a row, which hadn't been won before. And then we've also expanded that into various other fields of deep learning, computer vision, natural language processing, and healthcare data sets. So we are a unique organization where we have a sustainable, our business model is one where we create the bank money, which will create a ton of money for the bank. I'm actually surprised at how easy that was, both in the retail side and also in the capital markets. And then we spend a lot of our time in research, in improving our platform, and on healthcare efforts. So that's kind of us. But we have a good perspective of really the state of the art in deep learning and in machine learning. Now, going back to my comment earlier about enterprise prediction machines, right? So this is a product recommendation engine. This is a who's going to a trite, who's frauding me, who should I sell a mortgage to, is this person credit worthy? These are prediction algorithms using historical data. This is not deep learning. This has nothing to do with TensorFlow. Okay, so let me just ask the room here, who knows of gradient boosting machines? Okay, who here knows it well enough to take 2 minutes to explain it to the room? Okay, I think I think this is a problem. And if it's okay with you, if I could take 2 minutes to explain it. It's a very intuitive explanation. All right, so, but I'll explain the types of analytical processes that are deployed at large organizations, starting with regression models, linear or logistic regression models. Essentially what those are is you have this historical data set, and you're trying to look at that data, the historical data, to try to predict an outcome, and you split the data, and then you use the historical data and all those the inputs that you think are important, and you try to do this multidimensional line fitting. So to try to see, like, if it's a credit scoring model, actually, let me explain this in the context of recruiting. Okay, so recruiting is an easy thing that people kind of get to. So if you're tasked with building a model that an algorithm that makes a hire decision, then if you were to build a linear regression model in, say, fresh college graduates, you would build a model that takes the GPA, takes the type of degree, considers whether it's an Ivy League school, whether they did volunteer work or were in a college sport, give bonus points for those, and then add a factor for each and sum up the score, and then you have a score, and if they make the cutoff, you hire them. If not, you don't. And the weight of each factor is determined by the data set, and specifically what you look at is you look at the people you've hired fresh out of college, and see if they succeeded in a job a few years later, and if they did well, then that's a positive label. So linear regression model would work well in a cookie cutter scenario where everyone's the same, like fresh graduates, but it would not work for somebody who's got a lot of experience. If you're trying to hire a senior executive to the firm, you can't possibly treat them as numbers in an equation. So there, what you do is you interview them. You meet them and interview them, and you ask them a series of questions. Whatever they answer, you ask a set of questions, and then you find out that they were fired from their previous job. That will lead to a set of questions, right? So that would be considered a decision tree, right, in computer speak. So that would be a single, path you traverse down. And you can do better than that in a recruiting process. What you do is you get a recruiting committee, and everybody, 10 people interview the candidate. They all ask slightly different questions, and then you get together and you discuss the candidate. You have a broader view of them. That's actually a difficult thing to put into an algorithm, but there's one framework that's used. It's called random forest. Say if there's 100 questions you can ask to a candidate, what you do is you just randomly give those questions to 10 different interviewers, and then the stats kind of tell you what the weighting would be, and you get together. But again, that's not an intuitive process. Really, if a well-coordinated interview process is one where you'll have one area expert interview the candidate on this, and the next person on that, et cetera. And say in an organization, you're hiring a senior HR leader, then your chief HR officer, chief marketing officer, chief marketing officer and the COO's input matter a lot. The CTO's input doesn't matter a lot, right? So that's how you would do. Humans would intuitively follow this path. And what gradient boosting machine does, it actually does that. So what it does is it creates all these decision trees that focus on specific areas that they would, drill into. And machine learning will tell you how much weight to give to each one of those experts, what questions to ask, in which order, and how much weight each one of the answers provides. What weight you should give each one of the answers to the final predicted outcome. So these GBMs are a very intuitive way to use historical data and ask all kinds of questions. I'll talk a little bit about our credit scoring model. So our credit scoring model is a GBM, and it's the same as 1,000 loan officers, each asking 10 questions about the applicant and drilling very, very deep into that applicant. So you know everything about them, and basically you can, whatever your historical data signal has, a GBM can pretty well get to that. This has nothing to do with neural networks. This is very different. But what it is, where it is similar, is that training a GBM is programming. So all this other stuff was statistics. This is programming. And it's an iterative process. That's where the gradient boosting is. Much like training neural networks, you look at gradients and then move the goalpost slightly that way. It is very similar, which makes it hard. And this is why companies haven't historically managed to do this yet. Just some historical context to this theory. GBMs the theory was put forward out of Berkeley in 1997. Stanford created an algorithmic framework around it in 99. And it was quickly deployed in Silicon Valley in 3-4 years later. The first implementation of this at scale that I saw was at Yahoo when we did spam filtering. It was like humans were impossible at following up with, like we had all these rules that said, okay, if it has Viagra and for sale, likely spam. But these, you just couldn't have an army of rule writers that kept up with the spammers, so we let the machines take over. So I think hopefully that gives you some perspective of how important this is. Certainly, deep learning is being used in an organization in different ways. It's being used for understanding dialogue with them. It's used for, say, in our case, like things like check fraud for computer vision applications, et cetera. But GBMs allow every large enterprise to extract value out of the data that they have in ways that wasn't possible before. And what's important here from a timeline perspective, like why is this now becoming available? I did this at Silicon Valley 17 years ago. Why are we only now deploying it in traditional industry? Number one is that's a reflection of tech and that wonderful Silicon Valley geography where people go from Stanford, from Berkeley into that environment, and these ideas are quickly percolated and applied. And the second one is just that it is hard, and there wasn't really tooling for it. Now, there are two things that have changed. There's an open source community that's created a lot of tooling that makes this available. There's a particular GBM model library called XGBoost, Extreme Gradient Boosting. It was launched only 5 years ago. So the first version of that became available in 2014. And I think the version, and it was still very early. So this is pretty recent. It's 5 years old. And the second one is there's a marketplace for the data science competitions called Kaggle, where enterprises put data and people compete on these things and release their source code and discuss their source code. So now there's both tooling and examples that people can draw on. Every enterprise will be now deploying these types of models. So it's actually like that wasn't discussed during the last 2 days, but I think from my perspective, very grounded in how industry is deploying machine learning, this is what's going on. So I'm going to talk about credit scoring model. This is actual work. Please don't take photos. I'm not sharing these slides publicly, but this is actually actual work at TD Bank. We were tasked out of the many. So let me just first talk about layer 6 at TD Bank. But the benefit that we've had is that we came through an acquisition which had the CEO's support, which meant that anything we wanted to do, anything we asked for, we had a quick way of getting that done. Not all organizations who try to build organically have the benefit of that. So we've certainly been able to deploy a lot of machine learning models into production. I think one of the most important ones at a bank is the credit decision. Banks borrow money on short term and make long-term lending decisions, and in the middle of that is a credit scoring decision. So the way that it works roughly is that you look at your historical data, you do training both in time and out of time, which means that you go through the historical data and go forward like this with historical data predicting some future event. And then you also withhold old data into the future and a set of customer bases to validate whether the model is robust or not. The more historical data you have, and just the more data you have, the more complex your models will become, and the better they are. And end to end, the process looks like for us it takes about 5-6 months to do one of these things. And we start with first trying to predict something simple, and then we add data set after data set. And you can kind of see how the model improves over time and improves with complexity. And what's particularly interesting here is that these are highly unbiased outcomes. So we're looking to predict the default in this case, which is about 0.5% of the population. And I could just tell you that I'm going to predict nobody will default, and that has a 99.5% accuracy. That sounds pretty good. But what you really care about is really predicting at high precision those, like, you want to zoom in on like the most likely people that will default, and then triage those individuals. So in this particular application, TD was looking at this is credit cards, and we were looking at whether to increase a credit limit or to renew a credit card. And that runs through this credit scoring model. And what they do is they want to flag the 10% of people who are likely to default and not extend that credit limit increase. And the previous model had a 40% recall rate on that. So basically saying, okay, give you a prediction machine, tell me which ones I should deny that increase to. And they captured 40% of the people. This machine learning model has an 84% recall rate, right? So this may not sound like it's astounding from a, so like when you look at like relative improvement as you continue to increase, there's a Rubicon you cross where it just becomes like massively important to the business. And you can start doing things automatically and actually take much more different kinds of business decisions based on the accuracy of these models. I'll give you another completely different example. In the US, it's customary to do customer acquisition through incentives, giving people $300 if they come and open up a checking account for you. Recently, JP Morgan Chase started to offer $500, and our economics just didn't make sense for us to do that. Well, the reason they can offer $500 and we can only offer $300 is that they have a better prediction machine knowing which customers to make that offer to and how to handle fraud. Because a lot of people just take that $300 and disappear. So if you already have a better handle on being able to predict who will disappear and who won't, then you can give a different incentive. And that changes the competitive landscape. Okay, so back to the credit scoring model. The other thing that's new about this is that now we can start incorporating a lot more data than before. I can't quite share how much data we included on this one, but on one of our other use cases where we try to predict who's going to get a mortgage, also a very important model. The old model, linear regression model, had 13 inputs. The new one has over 1,000, right? And it just shows that you can throw the kitchen sink of data at it, and it becomes much more predictive. Interesting here is that we have transaction data that we include where the previous model didn't. And that becomes important in a second. What I also want to show here, what's interesting here is I heard a lot of people in the earlier conversations talk about these black box models. Well, with gradient boosting, it's actually not a black box at all. This is a you can narrow down both on a population level on what signals matter and down to an individual. What are the inputs that drove that decision? So here we look at feature contribution. We can look at insights like bottom left, pretty intuitive insight like the more products a customer has with you, then it drives the predictive outcome. So here again, being a full service bank actually helps us because we know that the more you can deepen the relationship, the economics of everything changes. And then you can drill down to an individual customer and say, well, these particular factors really mattered for this customer, and just this bottom right slide shows that this customer had $25,000 in revolving credit across all banks. If they only had $20,000, then the prediction would have been quite different. So those kinds of insights are really amazing and were not available to the bank before. And unlike neural networks, this is not a black box at all. All right, so now you might say, but Tomi, I saw on the slide that you trained it from 2005 till 2008. Sounds like a very strong economy. How on earth is that robust to an economic downturn? And that's a very valid question that this room should be asking. The question we could ask is, okay, we're adding lots of complexity for a better model, but is that complexity going to create some systemic risk when something unanticipated happens in the future? And we tested it through two different ways. One is to look at the market correction in the fourth quarter of last year. So there was a big drop in S&P 500. And we noticed, this is a little hard to interpret, but you can see this kind of seasonality in default rates. And then if the model had been trained up on data up till August of 2018 and then frozen, how robust was the model on an ongoing basis. That's shown in that yellow, that solid line. And it shows that the model was robust throughout. And what's important to note is that what made it robust was the inclusion of transaction data. So transaction data is a much more real-time and behavioral read into somebody's financial health, right? So now let's unpack that a little bit. Okay, so systemic risk. Right now there's a massive systemic risk because we all rely on bureau data, FICO scores, right? And every bank uses the same data. And this data is old, very old, and you don't know what's hiding in it. So now the banks are able to throw a lot more data about the customer and increasingly transaction data to get an actual read on their behavior. And we can update this in real time, and every bank will have a different set of data they throw at the problem. So I would actually argue that the systemic risk that we have today in our over-reliance of credit bureaus will be reduced by the application of machine learning and the involvement of more data sets. There's another exercise we're doing currently which has to do with looking at real economic impacts. I was asked, would a credit model like this be robust to the Lehman collapse? If it was trained from 2002 till 2007, would it hold? And I would love to be able to answer that question, but I can't because frankly, the data going back to 2002 is junk. It's completely different than what the current data looks like. So we can't go back there. But what we can do is we can look at various geographic sectors, which are more where there has been an economic impact, some economic change, where we have coverage of data. One interesting one in Canada is the Alberta oil sands. So this is a boom-bust economy, greatly impacted by commodity prices, availability of oil carts, train cars to deliver oil, and the U.S. oil shale boom. So it went through this massive, it had this boom economy and then a massive collapse starting in 2015. So we're looking at that as a market, trading from 2012 to 2015 and seeing how the model will be impacted. None of these things are perfect, but being able to use these types of models lets you really test out the models in different regions with different economic scenarios. So, the other thing that it does is we can actually exclude a lot of data sets or serve a broader set of customers. Say customers that are new immigrants to the country or some people who are rebuilding their credit scores. You can actually quickly adopt the model and ignore one data set, still have high level of predictive accuracy, look at their transaction data and continue to base most of your conclusions based on how they're actually behaving and what they're transacting. So my hope is that models like these will more broadly make credit available to the world. Bias was discussed quite a bit, and this is a huge topic for us. The model needs to be fair. We need to be able to justify it. If you deny somebody of a loan, you have to be able to be transparent with them and tell them what they need to do to improve their situation. So we have ways to look at unfairness across different populations, male, female, race, geography, and make sure that all of those are accounted for. And if we find bias in it, then unfair bias, then we can actually have a principled way of adjusting for that to make sure that it's fair. And I would argue that this is a million times better than some white male loan adjudicator making that decision. And like you can now control this from the top of the organization and make sure and model and manage your kind of reputational risk profile in an area such as this much better with machine learning. Okay, so these were the findings in credit scoring. Machine learning is much better than linear regression. More data becomes more accurate, so that furthers larger organizations. transaction data is valuable in real time, and you can manage bias, and I think there's reduction in systemic risk. So moving forward, this is my last slide. I wanted to talk about some of the competitive dynamics. I think there's a huge thing that I haven't heard discussed here, which is around competition between companies. Because AI will tip the competitive dynamics in the favor of enterprises with scale in 3 ways. Number one is large companies have more data. Large companies with multiple lines of business have more orthogonal data sets, which means that the more views you have on a customer, the better you know them, the better you can serve them. So say somebody like Google, who has both your search history and your email record and your browsing history and your YouTube cat watching video history, et cetera, they have an advantage. But as does somebody like TD Bank that has various different lines of business compared to a monoline business. That's an important competitive outcome. And the third is that there's huge scarcity of talent, machine learning talent, and that machine learning talent will be attracted to organizations with critical scale. Now that will probably be, over time, the education system is trying to race up and fill that gap, but I think at least for the next 5 years, that gap will persist. So this to me means that large companies will, with the application of AI, they will be at a competitive advantage. So take the US financial service market. You have 4 big banks, JP Morgan, Wells Fargo, Citi, and Bank of America, that have a disproportionately share of assets and customers and profit. There's over 6,000 banks in the US. How are those regional banks going to survive as these large banks increasingly deploy AI and deliver their services digitally over the phone? You know, TD grew through a lot of acquisitions following the Lehman collapse in the US, so we're still relatively new in the US and still going through some of the integration pains. And some of that integration is imperfect. And there's a lot of customers that we may have in certain markets where our digital offering just isn't complete. And we have the saying there, which is people under age 40, they just bounce off. We get them in through some incentive or something, but if we don't have a good digital offering, they just bounce right off, never really start engaging. And I think that's a direct reflection of the fact that we can't serve them digitally. Right? So now if the most important thing in a world like this is to be able to give a personalized digital service to your clients that meets customers' expectations that they get in their use of Netflix and Spotify, these large traditional enterprises, they have to be very technically savvy. And I think that's the big difference that large organizations will have to undergo, become as competitive from a technology perspective as big tech companies from the West Coast. And I think that's going to play out in a massive way. But I also feel like competitive dynamics are so stacked now in the future world towards these big companies with assets and resources to throw at the problem. I think the one last point that I also want to make is privacy laws matter. And European, Canadian, US, and Chinese privacy laws are very different. And as well-meaning as, say, European privacy laws are, it's really expensive to comply with it. And it's also very hard for companies to get access to data. In Canada, there's a privacy law that's an opt-in model. So you have to opt in to have you have to give the enterprise permission to share your data. And in the US, it's an opt-out model. Of course, nobody opts in or opts out. So the practical outcome of that is that in Canada, you just don't have access to any data outside of the first-party data that you own. In the US, there are data aggregators that know so much about you. I mean, there are data aggregators like Experian and Epsilon that know every household, what pharmaceutical prescription medication they are on, what they purchased. I mean, it is ridiculous how much they know. And I'm amazed that Americans don't feel that that's wrong. But in some ways, you think from a consumer perspective, that's a problem. But from a competitive perspective, it actually helps level the playing field. Everybody has access to that data. So I think that these types of conversations actually drive economic policy and the competitiveness of markets. Well, that's a lot of talking from an engineer. Yeah, thank you.
We have time for about 2 or 3 questions.
Over here.
So you mentioned about the competition between big companies. However, that there are still big companies in traditional industry, which they are incumbents already. So do you have anything talking about like the competition between giant companies in traditional industries and giant companies in tech industries? Because we now know that a lot of tech companies are trying to enter in some traditional industries, which is impossible to imagine before.
Oh yes, I think big traditional industry is absolutely terrified of Amazon specifically, I think is setting the stage. But a lot of these big traditional tech companies going into traditional industry, Apple Pay or Google Pay, they're the same. So yes, big traditional industry is very concerned about where the long-term intentions of big tech are. Mm-hmm. Jack.
I found your example about the $500 versus sort of $300 giveaway really interesting, because it seems like that bank was able to outthink you as a consequence of like scale. And I'm wondering, from a sort of policy perspective, how can you talk about this without access to sort of privileged information from inside these entities? What is the case that you can give to policymakers to say, we need to look at how firms have an ability to like outthink each other as a consequence of scale, because this factors into competition law? It seems like a hard thing to bring out, but very important.
Judging from your British accent, UK has been a leader in open banking, and it has completely changed the market dynamics in the UK. So I think that's actually an interesting point of view of how you can make markets more competitive through regulation. I think in the US, it kind of gets open banking you get around open banking through the privacy laws, but I would rather have this sharing of information be something that's actually constitutionalized in law. Yeah, over there.
Thank you. So thank you for a really interesting and impressive talk. I wanted to go back to your discussion of systemic risk. So I think you're absolutely right that it's extremely desirable to diversify your information sources in order to reduce that risk. And it allows you to better predict the cross-section of risk. Now, there is a flip side to that, which is if you have a lower riskiness along the cross-section, the temptation to reduce safety cushions is extremely high. And that may come back when the time dimension of risk hits you, meaning when you have the next big downturn.
Yes.
And you do have these lower cushions.
Yeah, and that is, you kind of hit it right on. As every company deploys machine learning, they'll see these models are more accurate than the others. We are also working on fraud models. So both this ability to predict whether somebody will go into financial distress or whether they're frauding you, they go hand in hand. Both of those will get better with machine learning. And so a bank will say, well, great, okay, now I can reduce my margins, right? And I think that's why it's important to also look at these, like to build a cushion and to really be able to model what that cushion is. That's why we're doing this exercise in Alberta right now to look at, what does doubling of unemployment rate do to your models. I would love to go back to the credit collapse, but we really need to be able to model those and build that appropriate cushion in. But yes, you're absolutely right. Like when everybody deploys this, it will reduce everybody's margin significantly. Yeah. Mara.
Quick question. You said you guys came in with 16 and they have 1,600 data analysts.
Yeah.
And they were much more productive than them. So, okay, so the question is they came in with 16 members of layer 6 and TD had a team of 1,600 data analysts. So does that, and we talked a lot about which jobs are going to be replaced by machine learning. So are the first jobs that are going to be replaced the data analysts? I mean, it's a bit of a silly
Yeah.
question, but I'm wondering, is that are those we talked about, secretaries, and we talked about all sorts of jobs and the age profile of those jobs. But are the first people you're going to replace the people who do what you do not as well? Is it the data analysts?
Yeah, no.
No. Okay.
No, that's not, no, because actually we're able to, so when you create a massive amount of value from data, then people will like data analysts generally. So more and more will tip towards like creating value out of data. But there is certainly a lot of people there that just don't have the skill set required to do machine learning. But broadly, like, the people at TD will survive because we're creating value, we're transforming the bank. I think that there's going to be lots of job losses, not because individually one bank will start making a decision that this type of job is no longer required, but more because I think the competitive dynamics will change. So in Canada, we have 5 big banks, 6 if you include National Bank. Like, really, in 10 years' time, are we really going to continue at that, have 5, 6 banks here in this market the size of California? So I think the more likely a scenario will be that some banks break out, other ones don't, and that's where you'll see the job losses.
What are you seeing so far in the very early days? Are you seeing any jobs being affected? Just because there was so much talk about that.
Yeah.
at the
So I mean,
conference.
just to be clear, not a single one of my use cases has been about workforce replacement. So I don't get to choose the projects we work on, and those are very appealing projects. Okay.
All right, last question.
Hi, I'm the next speaker, and I'm going to talk about discrimination in credit scoring, so I hope you stay. But so how do you think about the proposition of you can add 1,000 variables to your model, and you can look at the least discriminating of this credit scoring with added 1,000 variables, and you could do this in hiring too, and say that that's complying with the law? How would you interpret that versus thinking about variable by variable in complying with the law on discrimination and your unbiasing?
Yeah, so we have identified 13 features. One of those is gender. In some cases, it's age and race that we do not include in our model. But a machine learning system will learn representative signals for those. So it's not just enough to exclude inputs into the model. You then also have to go back afterwards and say, well, for each one of those populations, you need to make sure that the model is fair to those and that you can justify that they are fair. If they're not fair, then you can adjust your treatment of them.
But by adjusting, you're adjusting scoring based on a variable that's on average correct, but it doesn't, according to the law, it doesn't adjust for each individual, right? Because you're creating scores. Mm-hmm. And that works on average to unwind bias, but it doesn't work on an individual basis in the law.
Okay.
Maybe after the next talk,
Yeah.
I hope you stay and we can chat.
But let me just address that a little bit. So in the US, there have been cases in the past of redlining, like things where certain populations just don't have access to credit. So redlining would be like, okay, this neighborhood, don't give them credit. Now, like, if we exclude the geographic boundary where the person lives, and you start including all these behavioral information about persons, then you will start seeing dots within there that will meet the bar. This is no different than, say, let's take it to a totally different context. Auto insurance, insurance for driving, so auto insurance.
60 seconds.
Yeah. It is socially acceptable that young men pay a higher premium than the average population, right? And we have some justification for that. But now that these insurance companies are adding telematics into their systems and driving behavior, such as abrupt braking, start to become more indicative, they can put less weight on the fact that on the age and the gender of the policyholder. So I think that real behavior, as we're getting from transaction data, will be more indicative of an individual, and we don't need to put as much weight on discriminatory factors. And I think then you can also justify that to a regulator by looking at the outcomes of the data.